All of us know that if you ever travel back in time, you should definitely not kill your grandfather. I mean, that's generally good advice even for those of us who remain fixed to the linear timeline, but it's especially good advice for those who don't want to create some kind of temporal paradox / rift in the space-time continuum. This problem, known as the grandfather paradox, presents the main problem of time travel. If you go back and prevent yourself from being born, how would you ever have been able to go back in time in the first place? Other time travel paradoxes, such as the bootstrap paradox, take the question in a different direction. Imagine you go to a bookstore and purchase yourself a copy of Hamlet. Then you step into the time machine, head back to Elizabethan England, and find a young William Shakespeare, who has yet to write his opus. You present him with the book, which he copies and distributes as his own. Centuries later, copies of his copy still exist, ending up in the bookstore that you purchased Hamlet from. Who, in this case, actually wrote the play? If your brain is starting to itch in a funny way, you've got the right idea. Hi, I'm Erin McCarthy, and this is The List Show. These time travel paradoxes have been the subject of countless sci-fi plots and are actually a hot topic of debate in the field of quantum physics. But they remain unresolved, as is evidenced by how many different answers get proposed for them. While possibly frustrating, this is the essence of paradoxes. Self-contradictory, logically impossible, or simply unanswerable questions that are likely to keep you up at night. Today I'm going to share with you a number of paradoxes that are sure to melt your brain and mine, from a very conflicted Pinocchio to a hotel with infinite rooms. Let's get started. One of the more famous paradoxes, thanks in part to the Marvel show WandaVision, is the Ship of Theseus paradox. Here's a brief summary. Theseus was a mythical king and the hero of Athens. He was the guy who slayed the Minotaur, amongst other feats. He did a lot of sailing, and his famed ship was eventually kept in an Athenian harbor as a sort of memorial / museum piece. As time went on, the ship's wood began to rot in various places. Those wooden pieces would be replaced one by one. The process of replacing rotten planks with new ones continued, at least in modern versions, until the entire ship was made up of new pieces of wood. This thought experiment asks the question, is this completely refurbished vessel still the Ship of Theseus? Let's take it a step further. What if someone else took all of the discarded original pieces of wood and reassembled them into a ship? Would this object be Theseus' ship? And if so, what do we make of the restored ship sitting in the harbor? This paradox is all about the nature of identity over time, and has been the study of philosophical discussions for thousands of years. It appears in other forms, such as the question of the grandfather's axe and Trigger's broom, both of which ask whether an object remains the same after all the aggregate parts have been replaced. The idea even expands to questions of personal identity. If a person changes drastically over time, so much so that who they are no longer matches any part of who they once were, are they still the same person? Another paradox about the vague nature of identity is the Sororities paradox. The premise is fairly simple. It generally involves a heap of sand. If you don't have a spare heap of sand on you, it'll suffice to simply imagine one in your head. Now let's take away a single grain of sand from the heap. It's still almost certainly a heap of sand. Now take away another grain. Still a heap. If we continue this enough times, eventually it will be down to one grain of sand, which is almost certainly not a heap anymore. When did the sand cease being a heap and start being something else? The Sororities paradox is all about the vagueness of language. Because the word heap doesn't have a specific quantity assigned to it, the nature of a heap is subjective. It also leads to false premises. For example, if you try the paradox in reverse, you start with a single grain of sand, which is not a heap. Then, one could argue that one grain of sand plus another grain of sand is also not a heap. Then 2 grains of sand plus another grain of sand is also not a heap. This continues until even the statement, "a million grains of sand is not a heap," which, as we know, does not make sense. The name of the paradox, Sororities, comes from the Greek word soros, which means heap or pile. It's often attributed to the Eubulides of Miletus, a logician from the 4th century BCE who was basically a paradox machine. Most of his paradoxes deal with semantic fallacies, like the horn paradox. If we accept the idea that what you have not lost, you have, then consider the fact that you have not lost your horns. Therefore, you must have horns. And yes, most of his paradoxes are just as infuriating. However, one of his more famous paradoxes, the liar paradox, is still discussed today. Here it is. This sentence is false. That's it. Just think about it for a minute. If the statement is true, then that means that the sentence is in fact false, as it claims. But that would then mean that the sentence is false. And if the sentence, "this sentence is false," then that means it's true. But if it's true that it's false, then Okay, you get the picture. It goes on and on forever. The liar's paradox has been discussed and adapted many times through history, eventually leading us to my favorite version, the Pinocchio paradox. It follows the same general structure, but with an added visual component for flair. Imagine Pinocchio uttering the statement, "My nose grows longer now." If he's telling the truth, then his nose should grow longer, like he said. But as we know, Pinocchio's nose only grows if he's telling a lie, which means that if his nose did grow longer, then the statement would have been false. But if "my nose grows longer now" is false, then it should not have grown in the first place. This version of the paradox was created in 2001 by philosopher Peter Eldridge Smith's 11-year-old daughter. Peter summarized it neatly like this: Pinocchio's nose will grow if and only if it does not. Another variant of the liar paradox actually helped shape language in the 16th century. A crocodile grabs a child from the banks of a river. His horrified mother is told by the croc that he will return the child only if the mother can correctly guess whether the crocodile will return him. If she guesses that he will be returned and she is correct, the croc will return him, no problem. If she is not correct, the crocodile will keep him. However, if she guesses that the crocodile will not return him, an interesting paradox occurs. If she is correct, then the crocodile must return the boy, but in doing so, breaks his word and now contradicts her answer. If she is incorrect and the crocodile actually was going to return the boy, he will now have to keep him, which means he's now breaking his word. Due to the popularity of this paradox, the word crocodilite came to be used to refer to any similarly paradoxical dilemma. The interesting number paradox is debatably not a paradox at all, though it's often called one, but we stumbled on it while researching the script and really wanted to share it with you. It basically goes to prove that all numbers are interesting, even the boring ones, which are actually interesting, of course, and not boring at all, because they're boring. Interesting in this case means it has something unique to it. For example, 1 is the first non-zero natural number. 2 is the smallest prime number. 3 is the first odd prime number. The list can go on and on until you reach the first uninteresting number. It doesn't have anything special or fascinating about it, but being the first uninteresting number you stumbled upon, it is, in fact, unique, and therefore interesting. This idea was born out of a discussion between the mathematicians Srinivasa Ramanujan and G.H. Hardy. Hardy remarked that the number of the taxicab he had recently ridden in, 1729, was a rather dull one. Ramanujan responded that it actually was interesting, being the smallest number that is the sum of two cubes in two different ways. Ah yes, of course, that's what I was about to say as well. While most paradoxes are presented through a spoken or written philosophical prompt, some are visual in nature. Take, for example, the Penrose Triangle. Just a warning, if you stare at it too long, it will brain your melt. No. It's an object that is described by one of its creators as impossibility in its purest form. But the weird part is you can build one and show it to people. Obviously, it's a trick of proportions and viewing angles, but even after you reveal the trick, people will still see it as an impossible triangle. Let's end today with a dizzying mathematical paradox that takes place in, of all places, a fancy hotel. Hilbert's paradox of the Grand Hotel is a famous thought experiment that is meant to show the counterintuitive nature of infinity. Imagine walking into a big, beautiful hotel looking for a room. How big? Infinitely big. This hotel has a countably infinite number of rooms. However, all the rooms are currently occupied by a countably infinite number of guests. Countably infinite means you can one-to-one attach a natural number to everything in the set. One might assume that the hotel would not be able to accommodate you, let alone more guests. But Hilbert's paradox proves that this is not the case. In order to accommodate you, the hotel could, hypothetically, move the guest in room 1 to room 2. Simultaneously, the guest in room 2 could be moved to room 3, and so on, which would move every guest from their current room, x, to a new room, x plus 1. As there are infinite rooms, everyone would get a new room. And now, room 1 is totally vacant. Enjoy your stay. Let's say 3,000 people arrive in one room. No problem. Just repeat the process, but instead of x plus 1, simply do x plus y. Y in this case being 3,000. What if a countably infinite number of people line up behind you, each of which wants a room? We have a solution to that too. The pattern would now be 2x. Simply move the guest in room 1 to room 2, the guest in room 2 to room 4, and the guest in room 3 to room 6, and so on. This would leave all the odd-numbered rooms open. So each new guest could take one of the newly vacated odd-numbered rooms, and the previous patrons would all be moved to the next even room. The basis of the Grand Hotel paradox is the idea of counterintuitive results that are still provably true. In this example, the statements, "there is a guest in every room," and "no more guests can be accommodated," are not the same thing because of the nature of infinity. In a normal set of numbers, such as the number of rooms in a normal hotel, the number of odd-numbered rooms would obviously be smaller than the total number of rooms. But in the case of infinity, this is not the case, as there are an infinite number of odd numbers and an infinite number of total numbers. This paradox was first introduced by philosopher David Hilbert in a 1924 lecture and has been used to demonstrate various principles of infinity ever since. Personally, the concept of infinity hurts my brain, and if I walked into the Grand Hotel and they told me all the rooms were occupied, I would simply go down the street to the nearest Holiday Inn. Thank you very much. Thanks for watching this episode of The List Show. I hope your brain hasn't melted into a big pile of goop like mine has. Let us know your favorite mind-boggling puzzle in the comments below, and I'll see you next time.